Great. One million years later. All right. So we've been talking a bit about the chain rule, I believe. Yes, we were, yeah. Okay. So let's look at this example, which I wanted to get started sooner. But let's say we have the following situation. We have W equal to the inverse tangent of x squared plus 3y, and x is equal to r squared times t, and y is equal to r times the natural log of t. And we're asked to find del w del r. And first of all, I'll point out this is a partial derivative because at the very kind of bottom level, our top function w depends on x and y, and then x and y each depend on r and t. So at the bottom, from the top to bottom, w depends on both r and t. So it is a partial derivative del w del r, not a regular derivative dw dr. In either event, we have to draw the little mapping. I suppose you don't have to draw the mapping. I think it's helpful to draw the mapping. So I see that w is written as a function of x and x and y are both depending on r and t. So x depends on r and depends on t, y depends on r and depends on t. So when I draw or when I write my chain rule for my partial derivative here, I'm just looking for all of the pathways to get me from W to R. So that's going to be del W del X times del X del R plus del W del Y times del Y del R. And then we actually have to find it, which is kind of annoying, but gotta do the math. So del W del X, we're taking the partial derivative of this function with respect to X. The derivative of the arctangent of some stuff is 1 over 1 plus your stuff squared times the derivative of your stuff. The derivative of x squared plus 3y is 2x if we're differentiating with respect to x, which we are, times del x del r, which is going to be 2r times t. Plus, then we get to do this piece. Del w del y is going to be the same first part. It's the 1 over 1 plus your stuff squared. But then we're going to multiply by the derivative of the inside stuff. And this time, the derivative of the inside stuff with respect to y is going to be 3. And then we're going to multiply by del y del r, which is going to be 1 times the natural log of t. So I would point out, it feels to me like a lot of this is kind of just bookkeeping, in that you have to be very precise and careful about what is what and what we're differentiating with respect to. So I would like you all to take a minute to find del w del t, or maybe more than a minute, maybe 2 minutes. I've already done part of it for you if you think about it. You already have the del w del x already there and the del w del y. So I would point out if I was doing this problem, I'm not even thinking about what I'm writing right here, really. I know that my del W del X here is the same as my del W del X here. I'm not actually doing the derivative. I'm just saying, cool, it's the same thing. I'm gonna write down the same thing. Like, don't waste your mental energy. And then your del X del T is going to be R squared times 1. And then your del W del Y is already written down for you. It's 1 over 1 plus x squared plus 3y squared times 3. Yes, I know I could put the 3 on top and all this stuff on top. I really don't mind putting it on top. I just like writing it to the side to kind of remind myself I'm really doing the chain, right? I'm doing my derivative of my outer function and then multiplying by the derivative of my inside function. So it's a good visual reminder for myself, but it also takes up more space. If you want to put it on top, that's totally fine. And then we multiply by our del y del t, which is going to be r times 1 over t. And that's the whole shebang. Um, One other thing I'll point out, kind of the annoying aspect of a problem like this, is that if they ask you to write your final answer in terms of your lowest level variables r and t, you do have to go then plug in x equal to r squared t and y equal to r natural log of t for every x and y. We usually don't ask that, but it could be asked and it's kind of a pain. But that's sometimes what you got. Yes.
Why do you have, or why is it del y del t instead of like dy?
Because in this example, unlike previous examples, y and x are depending on more than just one variable, right? And before, like in the previous last class, we had like x is a function of t and y is a function of t until we wrote down dx dt and dy dt because they were not partial derivatives. But here, when I'm taking the derivative of x with respect to t, it's a partial derivative because x depends on more than one variable. And again, no one really cares that much. But I'm glad you're asking. But no one's really paying attention to like if it's a del or a d. Yeah. Sure. So I'm really kind of just looking at each piece by piece. So I'm looking at W and seeing, okay, W is a function of X and Y. So from the top to the next level, I wrote W depends or is mapped to both X and Y. And then X depends on R and T, and Y fortunately depends on the same variables. So below X and Y, I write R and T, and then I have to have a path going from X to R and X to T, and also a path going from Y to R and Y to T. Yes, I would say not very often, but yes, that's certainly something that's possible. And so, well, sure, let's do an example like that. So let's say we have something like, sure, z equal to, what do I want to make up here? Sure, x cubed sine of y squared plus 1. And then we have the x is r squared plus s squared plus t to the third, and y is just r squared times natural log of s. So if I was going to draw this mapping, here's what I would have. I'd have z depending on both x and y. X depends on r, s, and t. Y depends on just r and s. So when I do this, I'm going to have r. Let's make sure that t is furthest away from y. So I'm going to have t, r, and s. X depends on all three of them. Y only depends on R and S. And this only is really going to come up if we ask to find del Z del T. So for example, if I ask to find del Z del R, no big deal. It's going to be kind of as usual. It's going to be all the paths from Z to R, which is del Z del X times del X del R plus del Z del Y times del y del r. And if we calculate this, let's see, del z del x is going to be 3x squared times sine of y squared plus 1. Del x del r is going to be 2r. And then del z del y is going to be x cubed times cosine of y squared plus 1 times 2y. And del y del r is going to be 2r times natural log of s. On the other hand, if we ask to find, say, del z del t, well, you can still imagine that y depends on t. There just aren't any t's in there. So when I write out my mapping, my only real pathway is del z del x times del x del t. If you felt compelled to write the other part, here's what's going to happen. You say, well, okay, there's kind of this pseudo map from y to t, even though y doesn't depend on t. But look at this. You're going to get del z del y, and then your del y del t. Well, there aren't any t's in y, meaning the derivative of y with respect to t is going to be what? Yeah. So the whole piece there is zero, which means we didn't even need to write it. So really, we shouldn't have gone that path, and we should just been like, yeah, cool. It's only the paths that get us from z to t. And then for z to t, there's only the one path, del z del x times del x del t. So then we're going to get del z del x, which is again 3x squared times sine of y squared plus 1 times del x del t, which is going to be 3t squared. Good question. Thank you. I like that. But I will say it's fairly atypical. Maybe with the next example we're going to do is an exception to that. Maybe not the next example, actually. Yeah, I don't love that. Let's skip that one for now. Sure. So the next example is going to bring us back around to the thing I said before about implicit differentiation, which was like a couple classes ago. So let's remind ourselves via an example. So let's say we have the following situation. Numbers. Who needs numbers? So our equation is x cubed plus y squared plus x times e to the y equal to 7. And that's what's going on here. Okay. And we're going to find dy dx just using regular old implicit differentiation from 21A. So let's see what we've got here. So we're going to get 3x squared plus, we're thinking of y as a function of x. So the derivative of y squared is going to be 2 times y times dy dx, or y prime is what I would probably actually write, but okay. And then the derivative of x e to the y, we're going to have to use the product rule because it's a function of x times a function of x. So it's going to be 1 times e to the y plus x times the derivative of e to the stuff is e to the stuff times the derivative of the stuff equal to the derivative of 7, which is 0. And then, as usual, we would group all the dy dx's on one side, everything else on the other side, factor and divide. So grouping all my dy dx's on one side, and I'm going to factor while I group. I'm going to have 2y plus x e to the y, all of that times dy dx. So I'm looking at this term here and this term here. And then on the other side, I'm going to put the negative 3x squared. I'm actually going to write it as negative 3x squared plus e to the y. Which I wouldn't normally do, but there's a good reason for this, which you'll see in a second. And then finally, solving for dy dx, we get that dy dx is equal to negative parentheses 3x squared plus e to the y divided by 2y plus x e to the y. You don't really need those parentheses because your negatives outside of your fraction, it distributes, but okay. Yeah. Say that one more time. It is a D. Yes, I'm definitely saying D, even if my D's look a little bit curly there. So yeah, those are D's. They might look like dells. Yeah. But we know it's a D because in this example, the only variable y could depend on is x. So it can only be a function of one variable. Okay, here's a whole other way of doing this, which most people, myself included, think this is less work. Now, the buildup is not less work, but the overall result is less work. So here's what we're going to do. We're going to bring everything to one side of the equation here. So, and really it's okay if you have a 7 over there, like as long as you have a constant on one side, you're fine. But it's safer just to always make the whole thing equal to 0. So we're going to rewrite this as x cubed plus y squared plus x e to the y minus 7 equal to 0. And what we're going to think about is we're going to say, cool, this here, this is our function of x and y. And notably, our function of x and y is equal to 0. And now we're going to, well, before I get too crazy here, I'm going to draw a map. But the idea is I'm going to take the derivative of both sides of this with respect to x. But to do that, I need my mapping. Well, I know that f depends on both x and y. But if we're trying to find dy dx, we are making the implicit assumption that y depends on x. Right? If you're finding dy dx, you're saying y is a function of x, and I want to know what the derivative of y is with respect to x. So I also have to have a little arrow going this way. So when I take the derivative of both sides of this equation, my del x of f of x comma y equal to the derivative of 0. Well, the right-hand side is just going to be 0 because the derivative of 0 is just 0. But the left-hand side, we get something interesting. So to take the derivative with respect to x, I have to find all the pathways from f to x. So it's either going to be just fx plus the other pathway, which is the derivative of f with respect to y, which I'm going to write as capital Fy, times the derivative of y with respect to x, which is dy dx. And now what this allows me to do is I can solve for dy dx in a very convenient way. I can say that the partial derivative of f with respect to y times dy dx is equal to negative partial derivative of f with respect to x, and then dividing both sides by fy, we get that the derivative dy dx is equal to the negative of the partial derivative of f with respect to x over the partial derivative of f with respect to y. So looking at this particular example, look at what we get. We get the dy, that's a dy dx is going to be the negative of the partial derivative of f with respect to x. That's going to be a 3x squared plus 0 plus 1 times e to the y over the partial derivative of f with respect to y, which is going to be a 0 plus a 2y plus an x times the derivative of e to the y is e to the y. Oh, that looks familiar. It's the same answer. It's kind of neat. So, in my opinion, and again, most people agree that this is a faster, easier way of finding an implicit derivative if you're asked to do so. And what's kind of even better about it is it really works for kind of any situation combination of variables. You'll see what I mean in a second. Question. Good question. Yeah, real good question. Do I have a good answer? I don't think so. Hmm. I mean, yeah, real good question. Do I have an answer? I think what I'm seeing here is essentially, if you look at this here, if you're taking the derivative with respect to x, if you're just looking at the x things, right, you're getting your 3x squared plus your 1 e to the y, which you're also getting when you take the derivative of this whole thing with respect to x, you're getting your 3x squared plus your 1 times e to the y. When you differentiate with respect to x for the y parts, you get your partial of y times dy dx. So really, I mean, I guess it really comes down to this. This is the relationship that's happening. Here's your implicit derivative, and here's the relationship between your implicit derivative dy dx and your partial derivatives. And so the relationship really is that. That is the relationship between your implicit derivative and your partial derivatives. It's that the implicit derivative is equal to, and I always think of it this way, it's the negative of the partials where the variables are flipped. So for example, if I said, given something like x cubed z to the fourth plus y squared equal to y cosine of z. Sorry, you can't see that at all. and we said find del y del z, and it is a del here, not a d, because in this situation, if I'm thinking of y as a function of the other variables, well, there's two other variables. So I'm saying y is a function of x and z, and then I'm asking to take the partial derivative of y with respect to z. Well, here's the good news. As long as you remember to make everything equal to zero, this is really, really easy to compute. So first step here, rewrite this as x cubed z to the fourth plus y squared minus y times cosine of z equal to zero. And call this, or at least think of this as your f of x comma y comma z. You don't really need the input, just your capital F. So then your del y del z is going to exactly be the negative of the quotient of partials that are flipped, meaning the partial of f with respect to z on top, the partial of f with respect to y on the bottom. And let's see what we get. We get negative, let's see, partial of f with respect to z is going to be x cubed times 4z cubed, which I would probably write as 4x cubed z cubed, but oh well. Derivative of y squared is zero as far as z is concerned. And the derivative of negative y cosine of z is going to be negative y times the derivative of cosine of z is negative sine of z. So it's going to be positive y sine of z. On the bottom, partial derivative of f with respect to y. So the derivative of x cubed z to the fourth is zero. The derivative of y squared is 2y. And the derivative of negative y times cosine of z is negative 1 times cosine of z. Probably easier than doing this implicitly. Partially because you probably don't remember doing implicit differentiation as well as you remember this. But yeah, that's kind of the whole story. It's kind of neat that it works. Let's see here. So sure. Oh yeah, let's look at this terrible thing here. So sometimes people like to ask questions that are purposely confusing, I feel like, to be honestly, like to be like frankly, like sometimes some of these questions are just like, let's make this as challenging as possible. So here's another chain rule problem, which is going to be interesting. So we're going to let W just be a function of X and Y. We're not telling you what it is. And we're going to say that X is a function of T is X naught plus A times T. And sorry, A1 times T, apologies. And Y as a function of T is going to be Y naught plus A2 times T. Already I don't like the feel of this problem. No numbers is never my preferred option here. So question one, find W prime of zero in terms of the function F and its derivatives. Great. So here's what we do. I do the usual thing when I have a function of a function or a function of things that are functions of things. I draw the mapping. So at the top level, you could either write W or F, or you could write W equals F if that's helpful. But really, W is what I'm thinking of here. W is depending on X and Y. X and Y are both depending on just the variable T. I'm not going to find W prime of zero to start off with. I'm just going to write dW dt, or if you prefer, W prime of T. And it is a regular derivative because at the base level, W just depends on T. And then usual chain rule stuff. It's going to be del W del X or del F del X because W is equal to. This is where I feel like it's kind of annoying, right? It's not, I'm not going to write del WX because I want to write in terms of F because they told me to. So it's del F del X times dx dt plus del F del Y times dy dt. I know it's kind of annoying. Let's let's observe a couple things here. If we're going to plug in 0, let's think about what we're going to get. So plug in 0 for t, we're going to get x of 0 is equal to x naught plus 0, which is kind of typical, right? X of 0 is x naught, and similarly, y of 0 is y naught. So if I'm plugging in 0 for t, I'm plugging in x naught and y naught for f. So kind of annoyingly, not very excitingly, my derivative when I plug in 0 is going to be my del f del x evaluated at x naught y naught times my dx dt. What is my dx dt? What's the derivative of x with respect to t? It used to be something I enjoyed on steak. A1. You guys, have you heard of A1 steak sauce? It's like a thing that still exists. I don't know. I haven't enjoyed it on steak for many years, but as a kid, loved some A1 steak sauce. A1 is your derivative of x with respect to t. And similarly, the second part here is going to be del f del y evaluated at x naught comma y naught times A2, the derivative of y with respect to t. This feels like a cumbersome notation here. You might prefer, and I might prefer to write this as the partial of f with respect to x evaluated at x naught comma y naught times A1 plus the partial of f with respect to y evaluated at x naught comma y naught times A2. The question? Yeah.
Specify which ones.
Yes, but I'll remind you, you shouldn't get too caught up in that detail. Like it is important, but it is not that important. But I'll point out that so the f, these are the del's because f depends on two variables. These are the d's because x and y only depend on the single variable t. And as you've noticed, I'm not very good about differentiating between my del's and my d's because it's not super important. But it's a little important, right? It's not important at all. Okay. Oh, there was some. Yeah. Interesting. So there's something else to say about this, but I kind of need to wait. Yeah, I should wait. Because really there's something else to talk about here. It's kind of cool. So, sorry, one sec. Where'd you go? So there's something in this problem that we want to, yeah, we have enough time. Sure. Okay, so where we're going after this chain rule stuff is directional derivatives, which I know I alluded to last class, where you're finding the derivative of your function in any direction, not just in the x direction or the y direction. So this takes a little bit of buildup, but I think it is worth the time, and I feel like we have just enough time to do it. So you might, I don't know, you might want to write this down, you might not want to write this down. But let's take a look at the mountain that I was using a while ago, which is my favorite upside down paraboloid, f of xy equal to 9 minus x squared minus y squared. And we're going to look at the same point we were looking at before, which is the point on the level curve z equal to 4. And it's the point where, I guess I could draw my axes here. Sorry, I'm going to be a little lazy with things here. There's my z-axis, there's my x-axis, there's my y-axis. We were looking at the point 1, comma 2, comma 4. And last time we found that the partial derivative of x at 1, comma 2, comma 4 was just equal to -2 times the x value, which is 1, which is -2, and the partial derivative in the y direction at 1, comma 2, comma 4 was -2 times 2, which was -4. But now we're really interested in finding the partial derivative, or I should say the directional derivative in some other direction. Like for example, what if I want to know the slope of the surface in the direction of the vector. Let's see, let's say v equal to 2i plus 3j. Okay, well, let's look at this from the top view. So here's my x, here's my y. Drawing it this way. Here's my level curve. And I'm looking at the point where x is 1 and y is 2. So I'm looking right there. And I'm trying to point in the direction that's over 2 and up 3. So over 2, up 3. And even though I've drawn it a little misleadingly, I feel like, I just want to point out that that vector is not perpendicular to my circle. I know it kind of looks like it the way I've drawn it, but it is not actually perpendicular to the circle there. Not that that's important that whether it is or isn't, but being perpendicular has a special quality, so I don't want to lead you astray here. Okay, so this is where I think things get a little bit interesting. So this vector here, we actually want this to be a unit vector. So instead of using the vector v equal to 2i plus 3j, we're going to unitize or normalize v by dividing it by its own magnitude to get that u is equal to the vector 2 over the square root of 13i plus 3 over the square root of 13j. Because the magnitude is the square root of 13. Okay, this takes a little bit of buildup, but I promise you we're going to get there. So we're trying to find the derivative or the slope of this surface if we are moving in this direction that's kind of out away from the surface. So it's not going to look great when I draw it here, but we're saying, right, we're over here, over here. We're kind of moving in that direction, like in the positive x and the positive y direction, but still in the same plane, z equal to 4, right? We're not going up or down. Well, I should say, we're imagining moving outwards, and then by moving outwards, we're going to have to move down the surface or up the surface. It'll be down the surface because we're moving in the outward direction. So that's kind of the idea. Is you ask yourself, if I move straight away this way, what happens to my elevation? Do I go down or do I go up? And by how much? If I move 1 unit in the particular direction I'm looking at, that's why it needs to be 1 unit. Because usually when you're talking about slope, you're saying how much is your function changing as your x changes by 1 unit. And you're like, oh, my function is changing by like 5, so my slope is 5 over 1. Okay, so two things we need. We need maybe just one thing. We need the equation of this line that goes to this point here. So that goes through this point and this vector here. Luckily, we know how to do this. We know how to find the equation of a line parametrically given a point and a direction. Our line equation is going to be that x of t is, well, that point there was 1 comma 2. So it's going to be 1 plus how much we're moving in the x direction, which is 2 over root 13 times t. My y of t is going to be 2 plus 3 over root 13 times t. And that will give us any point on this line. All right, so now I want to find I think part of the reason I think this is so cool is because when I learned about directional derivatives as a student, it felt very like, what the hell is going on? Like, why does this equation work? And I feel like what we're doing here is we're kind of really explaining why you get the equation you get. So we want to find the derivative of f, or the rate of change of f in the direction of the vector u. I know I've said that already, but I just want to make it clear. So look at what we're going to do. We're going to say that my derivative, my df dt, yeah, df dt, not del f dt, right? Because I'm thinking, oh my gosh, I'm thinking my paper's in the way. I'm thinking I'm traveling along this line as t increases, right? So I want to know that as t is getting bigger, what's the slope of my surface? Okay, here's where the magic happens. So my del f del t, I'm going to use the chain rule. F depends on x and y, and x and y both depend on t. So it's the usual kind of df dt is equal to del f del x times dx dt plus del f del y times dy dt, which might not seem super exciting at first, but I'm going to write this as a dot product of two vectors. So it's the dot product of the first vector, del f del x comma del f del y. There's a special name for that vector. We'll talk about it in a moment. And the second vector is dx dt comma dy dt. Okay, but here's the deal. This vector here, if you look at dx dt is 2 over root 13. And dy dt is 3 over 3 root 3. 3 over 3. Oh my God. Dy dt is the other number. 3 over the square root of 13. Or more specifically, this is the vector u. This vector over here, the vector consisting of partial derivatives of your function in the appropriate order, x before y before z, this is called the gradient of f. And this is how you calculate the directional derivative of f in any direction u. The directional derivative of f in the direction of u is equal to the gradient of f dotted with the unit vector in your direction. It's kind of cool. It's not hard to calculate at all, which is kind of great. I mean, okay, sometimes it's kind of hard to calculate, but like it's not that bad to calculate. So in this example, our gradient of f, well, our gradient was, if we look at our function f, right, it's been a minute, f is the function 9 minus x squared minus y squared. So our gradient of f is negative 2x comma negative 2y. And we're going to dot that with our vector u, which is 2 over root 13 comma 3 over root 13. Now, this would be the directional derivative in this direction at any point on the surface. But we are specifically interested in the point 1, comma 2, comma 4. So the directional derivative evaluated at the point 1, comma 2, comma 4 is going to be negative 2 times 1, comma negative 2 times 2, dotted with 2 over root 13, comma 3 over root 13. Finally, putting it all together, we end up getting negative 2 times 2 over root 13, which is negative 4 over root 13, plus negative 4 times 3 is negative 12 over root 13. So we get negative 16 over the square root of 13, or something maybe a little bit bigger than 5. And that is the slope of the surface at that point in that direction. So if I was standing on the hill here at that point and I move in this direction, we're going to be going down the hill and our slope is going to be pretty steep. Cool. So yeah, question. Well, because it's convenient, really, because I recognized that this looked like I had dotted two things together, right? Because the dot product of two vectors is the first component times the first component plus the second component times the second component. But really, it's because I know what that the formula is, and I was kind of reverse engineering it. So there's some really kind of interesting things that come about because of this. One, well, actually, so I'll point out here. So observe that if your directional derivative in the direction of u of the function f is equal to the gradient of f dotted with u, well, you can also calculate this the other way we calculate the dot product, which is that it's equal to the magnitude of your gradient vector times the magnitude of your unit vector, which I think you all know what that is, times cosine of the angle between them. What's the magnitude of this vector u? It's got to equal 1 because it's a unit vector. So when you're calculating a directional derivative, if the direction vector you're given is not a unit vector, your first job is to unitize or normalize it. So for example, if I asked what is the derivative of the same function as before of f of x comma y equal to 9 minus x squared minus y squared, still at the same point, 1 comma 2 comma 4, but now in the direction of v equal to negative 13, sorry, negative 12 comma 5, I can't just dot my gradient vector with that vector. I have to first say, okay, well, my unit direction vector is going to be v divided by the magnitude of v, which is negative 12 comma 5 divided by the square root of negative 12 squared plus 5 squared, which is going to be 13. So I'm going to get negative 12 over 13 comma 5 over 13. That's my unit vector in the same direction as my original vector I want to find the directional derivative in. So then I would say my directional derivative here is going to equal my gradient of f evaluated at 1 comma 2 comma 4 dotted with my vector u, which in this case my gradient is still going to be the same as it was before because it's the same function gradient at the same point. So it's still going to be negative 2x plugging in 1 for x and negative 2y plugging in 2 for y. But now we're dotting it with this new unit vector, negative 12, 13, comma 5, 13, which is equal to negative 3 times 12 is 24, negative 4 times 5 is negative 20, 24 minus 20 over 13, or 4 over 13. So a much gentler slope in that direction. Okay. We're probably, in fact, if you look back at our picture here, right, our direction being negative 12, 5, we're going left and up. So we're kind of going like that way. So you can see we're not traveling like straight down the hill or straight up the hill. We're traveling kind of sideways around the hill, like on a nice switchback or something. But what I was trying to say over here was that based on this, you can see two things without too much trouble. The first thing is the maximum value of the directional derivative is the gradient, the magnitude of the gradient. So the maximum value of the directional derivative in whatever direction you're talking about is going to be, well, the magnitude of the gradient times 1 times what's the maximum value for cosine of theta? 1. Oh, look, the maximum value of your directional derivative is the gradient of f. That's probably the less interesting piece of information. The more interesting piece of information is that the maximum value of your directional derivative occurs in the direction of the gradient. Or in other words, the direction of the gradient is always the direction that the slope is the steepest. Meaning most positive. And then, well, that was not bad. Why would that be true? Well, if you think about what angle you need for cosine to be equal to 1, what angle do you need for cosine to be equal to 1? Right. And if the angle between your gradient vector and your direction vector is 0, they are pointing in the same direction. So you get the maximal value of your directional derivative when the direction you're pointing in is the same direction as your gradient. Kind of interesting. So if you think about this in terms of level curves being how your elevation changes, what ends up happening is your gradient points in the direction that is perpendicular to your level curves. Because if you cross level curves the fastest, your values get larger as quickly as possible, meaning your derivative is as large as possible. So it comes up a lot that the gradient is always the direction of steepest increase or fastest increase. And it's always perpendicular to your level curves or your whatever else you call them, your level curves, your elevation, your contours. That's what I'm looking for. All right. Oh, my battery's running low because I didn't plug it in because I was unplugging it. Don't do it. Safe. All right. All right, that's all I got. Have a lovely rest of your day. I don't know why it's making that weird little camera thing there, but okay. Didn't like what I just did.